Welcome back. This is Calculus 3 with Professor Hefe. We're in Anton's book, 11th edition, I believe. This is chapter 11, section 4, cross product. We're going to look at the magnitude of the cross product and a little bit more. We will give you the rules. We'll give examples, and then I'm going to go back and do the proof of each example. So if we start off with two vectors, u and v, and neither of them is the zero vector, and we have the angle between them makes the angle theta. The rules are the magnitude of u cross v is the magnitude of u times the magnitude of v times sine theta. So it's kind of like the dot product, but instead of cosine theta, is sine theta. In fact, it's identical to the dot product. You just change out which trig function with the multiplication type. The area of a parallelogram with sides u and v is the magnitude of u cross v. And u cross v equals the zero vector if and only if u is parallel to v, which means u and v, one of them is a scalar multiple of the other. Okay? So I will pull that away. We got some nice long proof I'll come back to in a second. I didn't write these in the order I want, so this is how we're going to do it. We're going to find the area of triangle ABC. If point A is negative 2, 2, 1, point B is negative 4, 5, 4, and point C is negative 2, 6, negative 3. So we can make the triangle. A parallelogram would be extending the sides, and I can see these two are equal because this is AC right here, and this is AB right here. If we did 8 vectors. So these two triangles are similar or identical in area, so the area is going to be 1/2 the parallelogram of AB and AC. So let's figure out what AB and AC are first. If we're going from A to B, we subtract the components of A from B. So we've got negative 4 minus negative 2 gets us negative 2 here. I've got 5 minus 2 gets us our 3 here. And I've got 4 minus negative 1 gets us our 5 here. If I do the same thing with AC, I subtract A from C. So negative 2 minus negative 2 is just 0. 6 minus 2 is 4. And negative 3 minus negative 2 is negative 3 minus negative 1 is negative 2. So now I've got the vectors AB and AC. Okay, so to find the area, remember the area is the norm of the cross product. That's what we just, the rule we just said. This is an example of it. So we'll find the cross product and do the 1/2 of it. So I set it up. I've got IJK. I'm doing AB and I'm doing cross AC. Could I do AC cross AB? Think about that while we work through the problem. AB cross AC. I've got negative 2, 3, 5, 0, 4, 2. Subcomponents, remember, we still have the 1/2 out front. I've got 3 times negative 2 is negative 6 minus 20. So I'm going to have negative 26 in the J hat. For the J component, remember the minus sign up front. I've got negative 2 times 2 is negative 2 is 4. Minus 0, 4 minus 0 is 4. I've got negative 4 there. And K hat, negative 2 times 4 is negative 8. Minus 0, negative 8 K hat. That's a vector. That doesn't give us an area. We need to take the norm of that vector. So negative 26, negative 4, negative 8, we take the norm. I've got negative 26 squared, negative 4 squared, negative 8 squared, 676, 16, and 64. They add up to 756. We still have the 1/2 out front. When you calculate it, this is approximately 13.75 units. Okay. The other two, using UV sine theta, shows up in later sections. And UV cross 0, or U cross V equaling 0. We can take a look at that in a little bit. Let's go back and do the proof though. So this is messy as hell. This is why I'm doing it last. It's very messy. So let's prove the first one. U cross V equals UV sine theta. I'm going to start with the right-hand side, UV sine theta, because I know what that is. I can rewrite sine theta as, remember, we've got sine squared theta plus cosine squared theta equals 1 from trigonometry. So sine theta is the square root of 1 minus cosine squared theta. Okay. So I'm going to rewrite the inside as cosine theta is the dot product. Remember, it's the dot product divided by the magnitude. So I'm going to do cosine theta is U dot V divided by magnitude of U, magnitude of V. And since it's squared, we're going to square each term. The next step over, I get a common denominator. Not a big change here. Pause this if you need to make sure you're following along with what I'm doing. So when I write out the inside, this is still here. I haven't wrote it down. I'm trying to save space in the writing of the screen. Don't forget that. But we're just doing the inside of the root right now. And we're looking at the, actually, notice the bottom of the root, square root, we've got U squared and V squared. The root on the bottom, U squared and V squared, turns into root, or norm of U, norm of V. These cancel. And we're just left with the U squared, V squared, the magnitude of U squared and magnitude of V squared, minus U dot V squared inside the radical. So that's what we're working on here. I got magnitude of U1 squared, or U squared, is U1 squared plus U2 squared plus U3 squared. Magnitude of V squared is V1 squared plus V2 squared plus V3 squared. There's a lot going on here, so you might need to pause it and work this shit out, make sure it makes sense to you. U dot V is U1 V1 plus U2 plus V2 plus U3 V3. Still haven't dealt with the square yet. So let's redo this where I deal with the square. These two are multiplied together. They make the top red line. Okay. I went component by component. U1 times V1, U1 times V2, and these are all squared. U1 times V3 squared. That's the first three here. Then U2 times V1, U2 times V2, U2 times V3. That's the second set of three. And this third set of three, notice I've got U3 on all of them. So that's the first half. And then we're subtracting the square of the dot product. That's the dot product right now. So when we square that, we get this line right here. What I've done is I've lined up the U1 V1 squared with its part above it, the U2 V2 squared with its part above it, and the U3 V3 squared with its part above it. There's also a lot of minus. These show up individually, but since there's two of them, I combined them already. I did a lot of combination in one step here. You might want to write this out just so you can see what's going on. But we got -2, -2, and -2 of each set of the combinations. Notice if we subtract, these parts go away. And we're left with, if I rearrange them in sets, I've got U2 V3 squared, and I'm going to do U3 V2 squared. Those two together are right here. We're going to put that with the U2 U3 V2 V3. I'm going to group them together. We'll see why in a second. Then I'm going to focus on the ones and the threes. So 1 and 3 is right here. U1 V3, not there. And U3 V1, and that's this set right here. So I group that right here. And finally, what's left over is the U1 V2, U2 V1, and minus 2 U1 U2 V1 V2. Put those together. These look a lot like a squared minus 2ab plus b squared. If I say a is U2 V3. Okay, and b is U3 V2, sorry. So that's a formula. That's a minus b squared. So I can rewrite that as U2 V3 minus U3 V2 squared plus U1 V3 minus U3 V1 squared plus U1 V2 minus U2 V1 squared. And what is that? These are the results of the cross product. When we square them and take the square root, we're actually finding the distance or the norm of it. Because remember, we had written out W equals, go back to a previous video if you didn't write them down, or if you wrote them down, check your notes. This is what we had. That was our W vector. So square each of these, sum them up, take the square root. That's this. That's the norm. So we started with UV sine theta way up here. We ended with U cross V. So we proved they're equal. Oh, I wrote there recall. Shit, I did that there. Let's go ahead and take a look at the other parts for P, B, and C, proving the parallelogram, proving this one. So the proof of B, if we write it out, we got the vector B here and the vector U here. The angle between them is theta. This leg right here is V sine theta, because this is the magnitude. So V sine theta doing the directional angle stuff. So area is like base times height. I could take this section over here and move it over here. And I have a base of the magnitude of U. The height is magnitude V sine theta. Magnitude of U times the magnitude of V sine theta. And what we just showed in the last section is that's U cross V. So the area of a parallelogram with vectors U and V and angle theta is such. Proof of C, if the cross product is 0, the two vectors are parallel or scalar multiples of each other. And we got to make the assumption that U doesn't equal 0 or V doesn't equal 0. Because if it does, it's just going to zero everything out. So if U cross V equals 0, then the norm of it equals 0. And then we know the norm of it is UV sine theta. The norm of the 0 vector is 0. UV sine theta, though, we know U isn't 0. We know V isn't 0. So sine theta has to equal 0. Since sine theta has to equal 0, theta is either 0 or pi radians, which is either parallel to or opposite direction. That's pi. So, bam, we've shown that U and V are parallel or scalar multiples of each other. If you want to do the other half of the if and only if, just reverse the direction you used to prove it. Start with sine theta equals 0 and work backwards. That'll be it for this video. Peace.